In December of 1972, 3 men stood in a valley on the moon that no human being had ever walked in before, and no human being has walked in since. The place was called Taurus-Littrow. Commander Eugene Cernan and geologist Harrison Schmitt spent 3 days there, collecting rocks, driving a lunar rover across the gray dust, and photographing something they didn't fully understand: a scattering of enormous boulders that had rolled down the slopes of the valley's mountains and come to rest frozen kilometers from where they started. At the time, the leading explanation was simple: meteorites. Something had struck the mountainside, shaken a boulder loose, and gravity did the rest. Case closed. Nobody thought twice about it for 50 years. But in 2025, a team led by planetary scientists Thomas Waters at the Smithsonian Institution and Nicholas Schmer at the University of Maryland went back to that data. The actual rock samples Cernan and Schmitt carried home, combined with decades of new orbital imagery, and they found something that meteorites can't explain. The boulders hadn't been knocked loose by something falling from space. They had been shaken loose from underneath, by the ground itself moving. The moon, it turns out, is not the dead, frozen, unchanging rock we grew up believing it was. It is still shrinking. It is still cracking. And in at least one place near where Apollo 17 landed, the ground has been slipping along an active fault for millions of years, possibly still slipping today. That's the secret hiding inside NASA's return to the moon. Not aliens, not a hoax. Something stranger in a way, because it's real, it's provable, and it directly threatens the very missions NASA is flying right now. Stick with me, because by the end of this, you'll understand why the ground under the next American astronauts to walk on the moon might not be as stable as anyone assumed, and why a second, completely separate discovery about lunar water ice just flipped what we thought we knew twice in the space of 2 months. Let's set the stage, because context matters here. On April 1st, 2026, NASA launched Artemis 2, the first crewed mission to fly around the moon in over 50 years. 4 astronauts rode the Orion spacecraft on a free return trajectory around the far side, the same basic path Apollo 8 flew in 1968, except this time captured in modern high-resolution imagery, streamed back to a planet that had almost forgotten what it looks like to see a human-crewed spacecraft leave low-Earth orbit behind entirely. The launch itself had been delayed from its original March target by a helium leak, fixed, rolled back to the pad, and flown. It worked. It worked well. That mission wasn't designed to land. It was designed to prove that Orion, its life support, its heat shield, its navigation, all of it, could carry astronauts safely around the moon and home again. It did. The next milestone is Artemis III, currently targeted for 2027 as a lander demonstration mission, with the actual crewed lunar landing, including the moon's south pole, a region no human has ever set foot in, targeted for early 2028. NASA announced the Artemis III crew in June 2026. Unlike the Apollo landings, which touched down near the moon's equator in relatively flat, well-understood terrain, this mission is aiming for one of the strangest and least explored regions of the lunar surface: the deep, permanently shadowed craters near the South Pole, where NASA hopes astronauts will find something Apollo never had access to: water. Beyond Artemis III, NASA has outlined plans for a permanent lunar base at the South Pole, built in phases, supporting long-duration crews for months or years at a time rather than 3-day sprints. NASA leadership has described this as a staged build-out. First, more frequent astronaut and cargo flights to establish basic infrastructure, then permanent surface systems for power, communication, and habitation, and eventually the kind of sustained human presence that starts to look less like an expedition and more like an outpost. That's the real ambition here. Not a flag and a photo, a foothold. It's worth pausing on how different that goal is from anything Apollo attempted. The 6 Apollo landings were, by design, short and self-contained. Get in, do the science, get out before consumables ran low. Nobody worried about what the ground might do to a habitat over 5 years, because there was never going to be a habitat sitting on the moon for 5 years. Artemis changes that equation completely. The moment you start talking about permanent structures, solar arrays, pressurized modules, and landing pads meant to survive repeated use over a decade or more, questions that used to be academic: is the ground stable? Is the water actually there? Is the site contaminated? Stop being academic. They become engineering requirements. That's the shift happening right now, largely out of public view, and it's the reason the discoveries in this video matter far more today than they would have mattered in 1972. And that ambition is exactly why the discovery buried in Apollo-era rock samples matters so much right now, because if you're planning to build permanent structures on the moon, habitats, power systems, landing pads meant to survive for years, you need to know one basic thing first: is the ground actually going to stay still? Here's how the discovery actually happened, because the process itself tells you something important about how real science works. Slowly, carefully, and through evidence, not guesswork. First, a bit of background on moonquakes themselves, because they're stranger than the name suggests. Scientists who study the moon's interior generally group moonquakes into four categories: deep moonquakes, which occur far below the surface, often 600 to 200 kilometers down, and are thought to be triggered by the tidal pull of Earth's gravity stretching and flexing the moon's interior; shallow moonquakes, which happen much closer to the surface, within the upper 100 kilometers of crust, and are the ones most often linked to active faults; impact-induced moonquakes caused by meteorites striking the surface; and thermal moonquakes, small, localized events caused by the extreme temperature swings between lunar day and night, which can crack rock and even rattle old hardware left behind by the Apollo missions. It's the second category, shallow, fault-driven moonquakes, that the Waters and Schmer research zeroes in on, because those are the ones capable of physically shaking loose multi-ton boulders on a hillside. Back in 2019, Waters led an earlier study, published in the journal Nature Geoscience, that went back through the seismic data recorded by the Apollo missions between 1969 and 1977. Apollo astronauts had placed seismometers on the lunar surface, instruments meant to detect moonquakes, the lunar equivalent of earthquakes. Over those 8 years, the network picked up 28 shallow moonquakes. When Waters and his colleagues relocated the estimated epicenters of those quakes using modern analysis techniques, they found something odd. 8 of them occurred within about 30 kilometers of young geological fault lines called thrust faults. Cracks in the lunar crust formed as the moon's interior slowly cools and contracts, causing the surface to wrinkle and crack the way a grape wrinkles into a raisin. One of those quakes had an estimated epicenter just 13 kilometers from a specific fault called Lee-Lincoln, which runs directly through the Taurus-Littrow Valley, the valley where Apollo 17 landed. There was another clue buried in the numbers. 6 of those 8 quakes happened when the moon was at or near apogee, the point in its orbit where it's farthest from Earth, and where tidal stress on the moon's crust is at its most extreme. That's not a coincidence you'd expect from random impact events. That's the signature of a fault line responding to mechanical stress, the same way faults on Earth do. That 2019 study raised the possibility. It didn't prove it. The Apollo seismic network was sparse, and the epicenter estimates were broad, good enough to point in a direction, not good enough to draw a conclusion. So Waters and Schmer went looking for physical, on-the-ground evidence instead. And this is where the Apollo 17 boulders come back in. Using cosmic ray exposure dating, a technique that measures how long a rock's surface has been exposed to space radiation, which tells you roughly when it stopped moving, combined with measurements of boulder size, the slope of the terrain, and computer simulations of how seismic waves would travel through that specific valley, the team reconstructed a timeline. Their conclusion, published in a paper on July 30th, 2025, ground shaking from a series of moonquakes was the most likely cause behind 4 sampled boulder falls and 1 large landslide in the Taurus-Littrow Valley, with the Lee-Lincoln Fault as the probable source. The events they reconstructed happened between roughly 90 million and 19 million years ago, ancient by human standards, but recent enough, geologically, that the same fault could plausibly still be active. Using data from NASA's Lunar Reconnaissance Orbiter, which has been circling the moon since 2009, mapping its surface in extraordinary detail, the team went further and estimated that a magnitude 3, 0 moonquake, roughly comparable to a minor earthquake here on Earth, rattles the Lee-Lincoln Fault about once every 6 million years. That might sound rare. But the orbiter has also identified thousands of similar young fault scarps scattered across the lunar surface, meaning Lee-Lincoln almost certainly isn't unique. It's one visible example of a process that may be happening quietly, slowly, all over the moon. To be precise about what the evidence does and doesn't show, this research did not capture the fault moving in real time in 2025, and it did not prove Lee-Lincoln has slipped since Apollo 17 left in 1972. What it did establish is a strong physical case that this fault, and others like it, have generated repeated moonquakes over millions of years, and that the underlying mechanism, a shrinking, contracting lunar interior, is ongoing. NASA's own science communications team, in describing the study, characterized young faults like this one as a class that could plausibly still be active today. Here's why that distinction matters, and why it isn't just an academic curiosity. The researchers didn't stop at interesting ancient event. They modeled what a moonquake near an active fault would do to modern infrastructure, and their findings carried a clear warning. Short missions like Apollo faced essentially no danger because astronauts were only on the surface for days. But long-term lunar bases, the kind NASA is actively planning for the South Pole, face a gradually increasing risk the longer they're exposed to a region with active seismic behavior. Taller, more top-heavy lander designs, including the kind of large human landing systems being developed for Artemis, may be especially vulnerable to ground acceleration if they're built too close to an active scarp. The researchers' practical recommendation was blunt. Don't build directly on top of a scarp or on a fault that shows signs of recent activity. The farther away, the lower the risk. It's not a reason to abandon lunar exploration. It's a reason to be far more careful about exactly where the first permanent human structures on the moon actually go. And that recommendation lands at exactly the moment NASA is finalizing where those structures will go. Because the primary landing zone under consideration for Artemis III and the future moon base isn't Taurus-Littrow, it's the lunar South Pole, a region NASA has never studied at this level of seismic detail before, and one scientists are now racing to assess using the same forecasting methods developed from the Lee-Lincoln findings, specifically because astronauts are heading there within the next 2 years. Now, here's the second thread, and it's arguably even stranger, because it isn't one discovery. It's a genuine, ongoing scientific argument playing out in real time, with major new findings landing just weeks apart and pointing in opposite directions. The reason NASA wants to land at the South Pole in the first place comes down to one resource: water. Not water you can see, not water you can walk up to. Water believed to be locked inside the coldest, darkest craters in the solar system, places called permanently shadowed regions, where the floor of a crater never receives a single ray of direct sunlight because of the moon's nearly flat axial tilt. Some of these craters have been sitting in uninterrupted darkness for billions of years. Temperatures inside can drop to around 25 degrees above absolute zero, roughly minus 248 degrees Celsius. At that temperature, water ice doesn't sublimate away into space. It can, in theory, sit there essentially forever. The idea isn't new. In 2009, NASA deliberately crashed the spent upper stage of a rocket into a crater called Cabeus near the South Pole and watched the resulting debris plume with a following spacecraft. That mission, called L-Cross, found water ice mixed into the ejected material. Researchers later estimated the concentration at around 6% by mass in that specific impact zone, direct physical confirmation that water exists in these shadowed craters. Since then, the working assumption in planetary science has leaned toward abundance. Some researchers estimated permanently shadowed regions could cover roughly 40,000 square kilometers across the moon's poles, with the majority in the southern polar region, and some models suggested ice concentrations as high as 20% within the near-surface material of craters like Cabeus. That was the assumption NASA built years of mission planning around. Then, in late March of 2026, a study using NASA's ShadowCam instrument, a camera built specifically to see inside permanently shadowed regions by capturing faint, scattered sunlight bouncing off nearby crater walls, flying aboard a Korea Aerospace Research Institute spacecraft, delivered a genuine surprise. Researchers from the University of Hawaii at Manoa, examining ShadowCam imagery, found no evidence of widespread water ice at concentrations above 20 to 30% by weight anywhere in the shadowed polar regions they surveyed. Instead of the broad, rich ice fields earlier models had suggested, the picture that emerged was patchy, small, scattered, isolated deposits rather than anything resembling a buried glacier. That was quietly a significant problem for mission planners. If water on the moon is scarce and scattered rather than abundant and concentrated, the entire logic of where to put a long-term base gets harder. You can't build a sustainable operation around a resource you can't reliably locate and extract. And then, just 2 months later in May 2026, a completely different research group using a completely different instrument published a finding that pointed the other way. Scientists at India's Physical Research Laboratory in Ahmedabad, analyzing radar data from the Chandrayaan-2 orbiter's dual-frequency synthetic aperture radar, a specialized instrument capable of probing beneath the lunar surface, not just imaging what's visible on top, identified radar signatures consistent with buried water ice inside a specific category of terrain scientists call doubly shadowed craters. These are small craters nested inside larger, permanently shadowed craters, shielded not just from direct sunlight but from indirect thermal radiation as well, the coldest, most isolated pockets of darkness that exist on the moon's surface. Of 4 such craters examined, one stood out, a roughly 1 kilometer wide crater sitting inside the much larger Faustini crater near the South Pole. Its rim showed lobate, flow-like features, the kind of formation researchers believe can form when an ancient impact punches through a layer of ice buried beneath the regolith, sending frozen material flowing outward like a scar. Combined with a strong radar reflection, it's some of the most compelling evidence yet for buried ice existing in a specific, mappable location. So which is it? Is the moon's south pole basically dry with only scattered traces of ice? Or does it hold real extractable deposits hiding in very specific, hard-to-reach, doubly shadowed pockets? The honest answer, the one a good scientist would actually give you, is probably both, depending on exactly where you look. Newer research published around the same period suggests the oldest, most persistently shadowed craters, the ones that have remained in darkness the longest, sometimes for 3 billion years, are the most likely to hold meaningful ice, while craters that have only recently fallen into shadow, as the moon's tilt slowly shifted over geologic time, are far less likely to have accumulated much at all. In other words, permanent shadow isn't a single simple category. Some shadows are ancient and ice-rich. Some are comparatively new and essentially barren. From orbit, they can look identical. On the ground, they may not be. That's not a failure of science. That's science working exactly the way it's supposed to. Competing data sets, competing instruments, competing teams, closing in on the truth by disagreeing with each other in public, using evidence until the picture sharpens. It also happens to be a far more interesting and far more honest story than any single dramatic reveal could be, because it shows you the actual texture of discovery. Contradiction, revision, and slow convergence. Not a single tidy answer handed down from on high. And it has direct, immediate consequences for Artemis the Thirst. NASA has to choose an actual landing site, a specific patch of lunar terrain, for the first crewed mission to the South Pole. That choice now has to account not just for terrain slope, solar illumination for power generation, and communication line of sight back to Earth, but also for exactly which permanently shadowed craters nearby are most likely to contain accessible, extractable ice, and which ones are essentially useless for that purpose. Get that decision right, and you've picked the cornerstone location for a genuine, sustainable lunar base. Get it wrong, and astronauts spend precious surface time and fuel chasing water that isn't there. It's also worth understanding why water matters this much in the first place, beyond the obvious need to keep astronauts alive. Split water into hydrogen and oxygen, and you have breathable air and drinkable water covered. But you also have rocket propellant. A source of water at the lunar South Pole could, in theory, let future missions refuel spacecraft on the moon itself, rather than hauling every drop of propellant up from Earth's deep gravity well. A difference that could make the entire economics of lunar and even Mars-bound missions fundamentally different. That's why India's ISRO and Japan's JAXA are jointly developing a dedicated mission called LUPEX, the Lunar Polar Exploration Mission, specifically to send a rover into these shadowed regions and directly sample what's actually there, rather than relying solely on orbital radar and camera data. The Chandrayaan-2 findings from Ahmedabad's Physical Research Laboratory are explicitly being used to help choose where that rover eventually lands, meaning the same doubly shadowed crater research feeding into NASA's Artemis planning is also shaping an entirely separate, internationally coordinated lunar water hunt happening in parallel. There's a third piece to this that connects the fault research and the ice research together, and it surfaced just weeks ago, in July 2026. A new study raised a concern that hadn't gotten much attention until now: spacecraft exhaust. Every lander that touches down on or near the moon's polar regions releases a plume of exhaust gas and vaporized propellant. In most places on the moon, that's inconsequential. It disperses into vacuum and is gone. But researchers now suggest that in the moon's most scientifically valuable regions, the very same permanently shadowed ultra-cold craters we've been discussing, that exhaust could behave very differently. Because those craters are so cold and so shielded from solar radiation, contaminants can potentially stick, accumulate, and persist for a very long time, rather than dispersing the way they would anywhere else. If that's correct, the increasing pace of lunar landings, robotic missions, Artemis test flights, eventually a base, could gradually coat the exact regions scientists most want to study in a thin layer of Earth and spacecraft-derived material, potentially masking or destroying delicate original signatures researchers are trying to read, including possible ancient clues relevant to understanding the early solar system and how water and organic material arrived on rocky planets in the first place. Put together, these three threads tell a genuinely striking story, one that doesn't need a single invented detail to be compelling. The moon we're returning to isn't the static, unchanging rock Apollo left behind in the popular imagination. It's a body that's still slowly shrinking and cracking under its own contracting interior, generating real seismic activity along fault lines that could threaten the very bases NASA hopes to build. Its water, arguably the single resource that makes a permanent lunar presence economically and logistically realistic, turns out to be far patchier and more elusive than early models suggested, hiding in specific pockets of ancient, undisturbed darkness that two rival datasets are still actively disagreeing about. And the very act of landing spacecraft to go study those pockets may be capable of contaminating them before we've even finished mapping what's there. So what does NASA do with all of this? In practical terms, this research directly feeds into landing site selection for Artemis III and the broader South Pole base architecture. Engineers now have to weigh geological hazard maps, built from the same modeling techniques used to forecast moonquakes along Lee Lincoln, against updated ice distribution maps built from ShadowCam and radar data, against contamination risk assessments for the exact same shadowed regions everyone wants to explore. It's a genuinely difficult, three-dimensional planning problem, and it's happening right now with a human crew's safety and a mission's scientific value both riding on getting it right. There's also a broader point worth sitting with. For decades, the popular image of the moon has been almost cartoonishly simple: A dead, gray, unchanging ball of rock, frozen in time since it formed over 4 billion years ago, with maybe a little bit of ice hiding in a crater somewhere. What Artemis-era research is actually revealing is a moon that's quietly, slowly active, geologically alive in a limited but real sense, with a water inventory that's genuinely uncertain and actively being remapped in real time by competing scientific teams using cutting-edge instruments most people have never heard of. That's not a smaller story than an alien signal or a secret base. In a lot of ways, it's a bigger one, because it's happening for real, it's testable, and it's shaping decisions that will determine exactly where the next human footprints on the moon actually land. 4 astronauts already flew around that moon in April 2026 and came home safely, having captured the far side in a level of detail no crewed mission ever had. A crew has already been named for the 2027 lander demonstration that follows. Sometime around 2028, if the current schedule holds, a human being will step onto the lunar South Pole for the very first time in history, into a region scientists still can't fully agree is rich with buried ice or largely dry, standing near geological faults that may or may not still be slipping today. In an environment, researchers are actively worried we might contaminate before we've finished studying it. That's the actual hidden secret sitting inside NASA's return to the moon. Not a monster in the dark. A genuinely unresolved scientific frontier unfolding in public, in real papers, from real institutions. The Smithsonian, the University of Maryland, NASA's own Lunar Reconnaissance Orbiter team, the University of Hawaii, India's Physical Research Laboratory, and Chandrayaan-2 mission, all racing, sometimes agreeing and sometimes contradicting each other, to answer a question that will define what human life on the moon actually looks like. We are going back to a world we thought we already understood, and finding out we barely understood it at all. Compare that to where we stood in December 1972, when Cernan and Schmidt closed the hatch on Apollo 17 and left the Taurus-Littrow Valley for the last time. At that moment, essentially everything we knew about the moon's geology came from 6 brief surface visits, a handful of seismometers, and whatever samples astronauts could carry back in a spacecraft with strict weight limits. It was an extraordinary amount of knowledge for the time, but it was also, by necessity, a snapshot. A few footprints worth of ground truth scattered across a world roughly the size of Africa. Everything else was inference, extrapolation, and educated guesswork. What's changed since then isn't just that we're going back with better rockets. It's that we're going back with over 50 years of orbital reconnaissance, radar mapping, and reanalysis of the original Apollo data using tools and techniques nobody in 1972 had access to. The Lunar Reconnaissance Orbiter alone has been circling the moon and building up its surface map for more than 15 years. ShadowCam has been staring into craters no camera could previously see into. Chandrayaan-2 has been quietly bouncing radar off the lunar subsurface since 2019. None of that existed during Apollo, all of it exists now, and all of it is converging right now on the 2 questions that matter most for anyone planning to live there. Where is the ground stable and where is the water? That convergence is itself part of the story worth telling. This isn't one lab making one announcement. It's Smithsonian geologists cross-checking their models against a public NASA orbiter archive, an Indian government space agency's radar data getting picked up and scrutinized by researchers on the other side of the planet, and a University of Hawaii team using a Korean-built camera flying on the same orbiter to arrive at a very different, competing conclusion. All within the same 12-month window, all feeding into decisions NASA has to make in the next 18 months. That's what modern planetary science actually looks like. Not a lone genius with a single dramatic reveal, but a loosely coordinated, occasionally contradictory, genuinely international effort to get the answer right, before it stops being theoretical and starts being a question of astronaut safety. So here's the question worth sitting with. When astronauts finally step onto the South Pole in 2028, what do you think they'll find first? Proof that the ice is really there, or proof that the ground beneath them is still moving? Let us know what you think in the comments. And if you want to be here when NASA announces the actual Artemis III landing site, which, based on everything we just walked through, is one of the most consequential real estate decisions in the history of exploration, make sure you're subscribed, because that announcement is coming, and it's going to tell us exactly how NASA weighed all of this.